In the next unit, we will look at string matching, which I called also what's behind Control F, what's behind all those find something in a text. We use that all the time, and it became smarter and better. But to start, we'll look at the basic problem and how to do that as fast as possible. But before we do that, I want to ask you a question that's already up on Pingo, which is basically just what's your prior exposure to any topics from this unit? Because I'm sure some of you might have seen it, but then again, unlike sorting, it's not quite part of the standard curriculum in all places. So even if you have an undergrad CS degree, you might or might not have seen this. And then some of you don't have a CS undergrad degree, so you might have never seen this. So if you tick none of the above in the question, that's totally fine. I just want to know how much time I should spend on some of this stuff. I don't think we need the 2 minutes, really. If you're all done, I would stop it. Is anyone still trying to remember all those things? OK. OK, that's roughly 70% said none. And then if you've seen one of these, you've seen all of 4, essentially. Yeah, so welcome again to the skiing lesson, including absolute beginners and, well, intermediate, semi-experts, whatever. I'll try to go through it slowly in some parts, but I will have to rush other parts. I will rush only those parts that are not on the exam, but otherwise we don't get through all of the material. But I guess otherwise it would be rushing through everything doesn't make sense. OK, let's get going with string matching. The first part is a bit about notation, formal notation, how we write formulas over strings. If you've never seen this, that will look a bit wild at first sight, but you will get accustomed to it, I promise. And then we'll look at a whole plethora of different algorithms for solving essentially all the same. They all solve the same problem, but they shed a little different light on how to do it. So they're all interesting in their own right. This unit is about strings. What's a string? It's a sequence of characters. So what's a character? That can be whatever you like it to be. It will usually be something that you type. Well, I'll come back to characters on the next slide anyways. So first, a bit of motivation why we want to work on strings. And in the time of the web, it's really the unique thing that everything gets mapped to. Almost anything on the web is based on text, whether it makes sense or not sometimes. We have lots of natural language text, obviously. That's clear. So a string can be just the text in a book. But we also have more esoteric types of texts, very specific types of texts like source code. And then, well, slightly more recently, we also have our own source code, if you like, which has lots of implications if you can search appropriately in DNA sequences and their relatives. Well, and ultimately, a bit string is also a string, just a sequence of zeros and ones. And anything you represent in a computer is a sequence of zeros and ones at the end of the day. So everything's a string. OK, seems to be very important. In this unit, we'll look at one specific problem, which is find the occurrences of a certain pattern string. So pattern might be misleading. It's just another string. So you hit Control F and you type some part of a word, and then your text editor finds all the matches in the text file you have opened. This is the problem I mean here. It's either called string matching or pattern matching. I try to go for string matching because pattern sounds like it could be something more general. And in this context, it's not. But there's slightly more general versions of this where you can where you can search for regular expressions. I'm sure you've heard of these. And some of the algorithms we'll discuss in this unit will actually immediately generalize to regular expressions in the formal language sense. But I will have to stop before we get to that point, really. All right. Let's get back to what is a string and what is a character, and if a string is a sequence of characters. We'll formally write sigma most of the time for a set of characters, and that can be whatever you want as characters, but it can be just our common letters from whatever script they come. It can be the union of all these. Unicode characters was an effort to have a single mapping from all the alphabet, all the symbols in all languages we have to bit strings, or well, to 4 bytes. And it can also be something more tailored to a specific application. It can be just the bits, or it can be just the amino acids. Sorry, this is not amino acids. Oh, they called for DNA and RNA. Shoot. OK, the 4 letters that you have in DNA. So whatever is appropriate for your application is the alphabet. We will usually assume that the alphabet is fixed and given and does not grow with your input size. Usually, that's our assumption. That's not always true, though. So that's something to keep in mind. That's why little sigma, the size of capital sigma, the number of different symbols, will sometimes occur in our analyses, because it could have an influence on how fast an algorithm is or how much space it needs. That was an alphabet. Now, what can we do with alphabets? We can form n tuples, and strings are essentially tuples. That's the same. It mathematically is the same thing. So that's why we write sigma and then superscript n for the set of all strings of length n over this given alphabet. Then there's sigma star, which is, well, the union of all those for any n. So that's just all strings, all finite strings. And sigma plus is the same thing, except it excludes this guy here, which is the empty string. There's only one, independent of which alphabet you work over. So we might as well reserve epsilon as a single symbol that we always use for the empty string. I don't think we'll use it a lot in this module, but it's standard notation. It's useful to know. Some more notation. If we have a string from a certain alphabet and it has a certain length, so this is a very short and terse way to say S is a string over sigma of exactly n letters. I will treat strings as arrays. So if we have such a string, we write S and in brackets I for the ith character, and I count it starting at 0, like for arrays. That would also mean this is written as S0 up to n minus 1. Okay, that's if you really want to be explicit about the array. And I made an effort to always put it that way as an array so that the size is explicit. And also to constantly remind you that we start counting at 0. All right, what can we do with strings? We can take them and glue them together and form a longer string, formerly called concatenation. That's where Unix cat comes from. What else? We can take a string and extract something. That's the inverse of concatenation, if you like. So you take a certain range from the string, and, well, that's just taking those characters. That's a substring. Specific substrings that have a specific name are the ones that start at 0 or end at the end. Those are called prefixes or suffixes of a string. And the last point is I will use the round parenthesis to say the endpoint is exclusive. That's convenient because then we can write 0 and exclusive for the thing that occurs most often. Okay. Questions about this? It's probably a slide you'll just come back to in case you forget. But to test your understanding and to wake you up again, a tiny question on this. Don't want to spend too much time on this. Okay, most of you got this right. That's exactly as I said. The sigma star is all the finite strings, including the empty one. Sigma plus is the same, just without the empty one. So if we added, these two are the same. Goodie. That was definitions on strings. One last slide on definitions. What is string matching? That's an algorithmic question, so we'll have an input. And the input is two strings. One is the text. Usually we'll think of that as a fairly long string. And the other thing is the pattern. That's the thing we look for. And again, it's called pattern, even though it's just a fixed string. It's not a pattern. Well, it's not a generic thing that could represent different strings. It's a single fixed string in this case. For the problem, I'll focus on the version that finds the first occurrence of the pattern string in the text string. Other variants that are studied are to find all occurrences at once. It depends on the application and on the algorithm which one looks more natural. I would argue it's fine if we take the first occurrence because we can always find the first one and then start from there, find the next one. If we talk about parallel algorithms, and we will next unit, then we might want to come back to finding all the occurrences at the same time. What happens if the thing doesn't occur in the text? Then we can't really return the position of the first match. Then we just return the special no match or -1 or some error code. All right. I probably should have done this as a question, but here's a small example. The first match of he in where is he is not actually here, but right here. That's why I is 1. The return value is 1. Remember, we start counting at 0. And well, if you search for something that's not in there, you get no match. If you're looking for an implementation of this in Java, it's called index of, which if you have a string, you try to find the index of another string. It makes sense to call it like that. So this is an algorithm that exists in the library. And as you'll see, the one they implement is not the most sophisticated one. Namely, it's this one. OK, very simple algorithm, but sometimes good enough. So before we look at concrete algorithms, a few general remarks how most of the algorithms in this unit will work. First of all, the whole of Unit 4 will be about string matching, and it will only look at the sequential case. And then next unit will look at the parallel string matching methods. So for this unit, you can forget about the PRAM and all this. The algorithms will always make guesses. That's a position in the text, a shift in the text at which, well, the pattern could occur. We don't know up front, but then we try to check a guess. which is one comparison of two characters. So, well, okay, don't get too obsessed with the formal notation. It'll be natural enough in the specific algorithms. But when I say guess, it means a position in the text that we currently think might be an occurrence of the pattern. And then the next steps will try to check whether or not that's true. A simple observation is if a guess I is correct, if the pattern actually occurs there, there's not really anything I can do around comparing all the characters of the pattern with the corresponding text characters. If I skip one, I never know if the text actually has the right symbol there. But if I have a guess that turns out to be incorrect, a single comparison that's a mismatch already disproves that this is a guess. So I can much more easily disprove than prove that a guess is correct. For most of the unit, we'll count symbol comparisons. So we'll compare individual characters in the text and in the pattern. And our cost measure will be the number of these checks. And then it's already clear, unless you do stupid redundant work, you should never do more than n times m checks. You should never compare more than every possible guess and every possible shift inside the pattern. Okay. And the brute force method essentially does that. It's just a very tiny bit smarter than that. That's why I'll jump right into the code. We iterate through all the guesses. I is the guess. That's the position in the text where the pattern might start. For each of these guesses, I go through my pattern, through all the characters in the pattern, and then I compare. If the character in the text at that position does not match the character in the pattern, so the character in the text does not match the character in the pattern, then that I have disproved this guess I, so I can skip the rest of this inner loop. That's what break inner loop means. Well, jump to line 5. If I found one mismatch, I can quit that loop and go to the next guess. But if I have a match, I have to continue checking the whole pattern. If at any point in time I found all the characters of a pattern, then I found the first match and I can return the guess that yielded this match. And if I go through the whole outer loop without ever finding a match, then there was no match. Okay, easy enough. It's essentially the method that Java uses, which also means that in many cases this is good enough. But there's cases where it's not. But let's look at a case where it's not that bad. Okay, since many of you haven't seen this before, maybe I'll go through this. Here's our text. And our pattern is ABBA. So my first guess is I equals 0. I would just go through this. I would find, but then I'd have a mismatch. So at that stage, I know, well, guess 0 wasn't successful. I have to go to the next one. Then I start comparing again. Already mismatch. I don't have to compare the rest of the pattern at this position. I can immediately forget about I equals 1. At I equals 2, same thing happens. I equals 3, same thing happens because the first character in the pattern is A. So here again, I start comparing A, B, again mismatch. Okay? You see how this works? And if you go through this, you'll find that in this case, you compare 15 characters in total before you found this first match. Whereas the worst thing that could have happened, n times m, is much bigger than that. So it's not that bad. So the good thing is brute force can be good enough for this very simple problem. So you might go for it as long as it's good enough. But it can also suck very badly, in particular for this specific example, which is a bit made up, I agree. If your text is just all A's and your pattern is all A's but one B at the end, you will always check all those characters, and then at the last position, oh, again a mismatch, surprise, oh, again a mismatch, how bad. The world has conspired against me. In that case, you do essentially this worst case number of comparisons. But if you look at this worst case, that seems very special. Maybe there's a way to exploit the special property of this input. And well, the second observation is here, well, we always started comparing from the beginning again. But as a human, we already knew that this was an A from the previous times. Maybe we can avoid that. And that's what we'll do. So that was like the appetizer for string matching. There's two main routes that we'll look into. And the first one, this will be what we'll talk about for the rest of today, and I guess also sometime on Monday. We will look at improving the brute force method by first closely looking at the pattern. Try to figure out if the pattern is special, like in our example, and what that means for string matching. And that will be some form of pre-processing of the pattern. And all of those algorithms essentially fall in that category, maybe Raven-Carp not so much. And the second approach is completely different. You could also pre-process the text instead of the pattern. This only makes sense if the text is fairly static and doesn't change all the time. But there's many texts out there that don't change all the time. We have lots of libraries, we have books, we have DNA, all of that. Well, if you have cancer, that's not quite true, but the hope is that DNA doesn't change so often. So there's lots of texts that don't change. So we can afford a lot of time to look at this text once, but then after we've done that, we can very quickly find patterns in that text. And we'll also look at that 2 units from now.